right. How's everybody doing? You guys always smile when I ask that question, but then nobody really gives me an answer. Some of you nod and some of you shake your heads, and a yes or no really isn't the answer to how are you doing, is it? So, well, anyway, it's week 5 Thursday, which means 1 week from today, it's all over, right? Like 1 week. So how many hours are in a week? 168? So I guess in 170 hours, we are all done, right? So, yeah, that's summer. Summer goes by so fast. Okay. So anyway, I have to figure out what to put on your final exam, which will be, in 7 days. And then I don't like to do like new stuff like right before the day of the final, which is a little bit of a shame because we effectively only get 9 days of lecture then, and I'm like talking about stuff right now. So next Tuesday, week 6 Tuesday, I think I'll cover stuff that I think is interesting and worthwhile to learn and cover, but it will be stuff that will not be covered on the final exam, okay? So we'll do it like that. But please come to class, all right? As soon as you say, like, this stuff's not going to be covered on the final, it's like people are like, all right, adios, I'm not going to see you. And so please come on Tuesday of week 6, despite my proclamation that the material on week 6 of Tuesday will not be on the final. I think it will be good for your learning. Okay, so on Tuesday we covered randomization tests and a little bit of Bootstrap, and I don't know, are there any questions before we move on? Okay, all right. Well then, let's talk then. So we have randomization tests, and Bootstrap tests, and these are both kind of class. These are sometimes known as resampling methods. Because that is effectively what we are doing, is we are resampling our sample. And so a randomization test is used when the data we have what? Yeah, when there's random assignment in kind of the process that generates our data, okay? When there's random assignment in the process to create our data. Okay, so i.e. random experiments. Okay, so if we've got random assignment in the process to create our data, random experiments, we can do a randomization test, all right? And the assumption is exchangeability, meaning that all permutations of basically the data to the treatment groups are equally likely if the null hypothesis is true. So that's the randomization test. Okay, we're assuming that during the creation of our data, we randomly assigned our subjects to different groups. And so we're saying, if we had done this on another date, it's entirely possible that the subjects ended up in this arrangement, this other permutation, which is just equally likely. And so all possible permutations are equally likely, and therefore, when we do the randomization test, we shuffle the observations to the different treatments. Okay. We shuffle the observations to the treatment groups. Okay, so let me just do kind of like we'll do another example here, okay? So here I'm going to just say, all right, so I will simulate some data, and here we actually get to see the data generation. Okay, so we will say, I don't know, what do we do? We'll create control, we'll have control group, and maybe we'll do 12 observations from the normal distribution where mean is equal to 100 and the standard deviation is equal to 10. Okay, and then we'll have the treatment group. Maybe we'll have 15 where the mean is 110 with a standard deviation of 12. Okay, and so you create, here's the control group. These are the observations here, and here are the treatment group over here. You can create a histogram of the control group. All right, and here's a histogram of the treatment group. Okay, and the question is, do we have evidence that the two groups have different means, right? So, based on our observations, we have evidence that the two groups, or that the respective populations have different means. Okay. So the traditional method would be to do a t.test, and we would do control group versus treatment group. You have your x and your y. Okay. Yeah, so we'll just go ahead and run that. And we get this p-value of 0.009577. So that's the your two-sample t-test. So here we would say we have evidence that the two means are different, right? Your traditional method, you would kind of calculate the mean of the control group and you get 97.7, and the mean of the treatment group, and you get 112. You're observing a difference of around 115-ish, 114.3, and not 100, 14.3 points. And we say, do we have evidence that they are different? Okay, and you would do a t-test, and you get a small p-value. Okay, let me I'm gonna just set seed here, and we'll redo this. Okay. Okay, so here, here we get a p-value of 0.05318, okay? So our p-value this time is 0.05318, so we might not reject the null hypothesis. Okay, if I did this again with a different random seed, maybe we would reject the null hypothesis, right? Let me just find another random seed here. Okay, so here we get something. Okay, this time our p-value is 0.01863, right? So we would probably reject the null hypothesis. Okay, and of course in any test, whether you do the traditional method or the randomization test, your conclusion is going to be based on the random data you observe, right? So in this first case with set seed 1, I got a mean of 102 versus 110. So we have a kind of an observed difference of around 8 points-ish, okay, around 8 points, and that corresponds to a p-value of 0.053, okay, based on the data we observed, okay? And then on another day, because we have small samples here, right? Here I have a slightly larger difference, okay? And we're getting a smaller p-value, okay? So in each of these cases, just the just always the case is the data we observe will influence the conclusion we make. Okay, so here let's go and just take a look at our we'll go back here and we'll do a randomization test. Okay. So here I generate my data once again. Okay, I've got a control group and I've got a treatment group. So these are my 12 observations in the control group, and these are my 15 observations in the treatment group. And we want to know, does this provide evidence that the two groups have different means? Okay. And so in the randomization test, we're not going to run a t-test. We're not going to do some kind of central limit theorem stuff. What we do is in the randomization test, what we do is we're just going to shuffle all of our observations and say these, now I have 27 observations. I'm going to just mix them up, throw some of them into group A and some of them into group B. 12 into group A and 15 into group B. Now we know, because I just shuffled them up, that there is no real relationship between what we observe in group A and what we observe in group B, that any difference we observe between those two groups is just from the random assignment alone. Okay, so in the randomization test, we shuffle all the observations together. Okay, so maybe I'll just create something called the pool, which will be the control group and the treatment group together. Okay, so the pool, we shuffle all of these together, and then the shuffled group will be, I'm going to take sample, pool, all right? So this just resamples the observations in pool, okay, without replacement. So when you just do sample, this is going to just shuffle all of those values together, okay? So here we have 27 observations, and they're all just shuffled, okay? And so now I just called, I'm going to just take the first 12 and put them into group A, and put the other ones, 13 through 27, into group B. Okay, so there is no real association between group assignment and value. Okay, if there appears to be an association between group assignment and value, it is purely by random coincidence. Okay, so now we can see what is the mean of group A. Here I get a mean of 106. What's the mean of group B? I get a mean of 107, which is kind of what we would expect. We expect, because I've just randomly shuffled these and I reassigned some to group A and some to group B, I would expect them to have means that are similar. Okay. And for the randomization test, is we would repeat this randomizing / shuffling process many times, and record how often the difference between means of the shuffled groups are as large as or greater than we have a word for this, greater than or equal to the difference observed in the real data. Okay, does that make sense? So all I'm going to do is just, I'm going to take this and throw this into a loop. So we're going to do for I in, I don't know, 1 through 10,000 or 100,000. Okay, so diff will be repeat NA, let's say 10 to the 5 times. We'll do okay. All right, so just taking a look at our code, I'm just creating a vector to store all of the shuffled differences that I get. And every time I do this, I'm going to shuffle my random sample, or my pooled data. Maybe just for reproducibility, I'll set a seed here. Okay, we're going to shuffle the 27 values. We arbitrarily assign the first 12 to group A, and then the other 15 to group B. Okay, we know that there's no association between group assignment and value. It's just pure coincidence from random shuffling. Okay, but even though it's random shuffling, there might still be a difference. Okay, and so we just record all of those differences. It runs for a couple minutes, not minutes, a few seconds. Okay, and now it's done. And we want to know how often are the differences we observed, how often are they greater than the difference we got in our data, right? So in our data, in the actual data, the mean of group, wait, this is different. Okay, so we have to do set seed 1. We get our control in our treatment group. Oh, okay, now that is correct. Okay, so these are the two means. Okay, and so our observed difference in the data is this. Okay, this is the observed difference in our data, which is a difference of negative 7.938. Okay, so for a two-sided test, that is to say mu1 is not equal to mu2, the alternative hypothesis is mu1 does not equal mu2, we want to see how often is the absolute value of our difference vector greater than or equal to the absolute value of our observed difference. Okay, so this is going to produce a true-false vector, so I just need to get the proportion. Okay, the proportion of our differences that were greater than the observed difference. Okay, so what is that proportion? We get a proportion of around 6%, 0.06364. Okay, so here we are not putting any kind of assumption of normality on the data, which is what we do when we do a t-test. Here we just shuffled the data, and we just said 12 of you are going into group A, 15 of you are going into group B. What's the mean of group A? What's the mean of group B? Okay. In the real data, the difference between group A and group B, that difference was 7.938. Okay. When we do this randomizing, how often do we get a difference of 7.938 or something more? Okay, this happened, I guess, 6,000 times out of 100,000. Okay, about 6% of the time. So now we have to make a judgment call. Do we reject or do we not reject the null hypothesis? This is basically our approximate p-value is 0.06364. Okay, and maybe we choose not to reject the null hypothesis. If we use alpha equal to 0.05. All right, or less. So if our alpha is 5% or less, we would not reject the null hypothesis in this situation. Let's save this. This will be randomization and Bootstrap Test code. Okay. So this is effectively the test, right? You just shuffle up your data, say some go into group A, some go into group B, and then you ask how often is this the randomized differences greater than or equal to our observed difference. Okay, and again, if your data was different on another day, you might get entirely different answers here. Okay, so here I have set seed 3. You just copy So if I did this here, Okay, we get a p-value of around 4%, okay? Versus when we did just the t-test for the same data, we got a p-value, you know, closer to 2%. Okay, so I mean they're similar and they're on the same order, but you're going to get differences. As your sample size increases, then the difference between a t-test and a randomization test will get smaller and smaller. Okay, because they're eventually going to kind of crash. So if I did 120 and 150, this will take a little bit longer. Okay, here I get a p-value of 0.01358, and if I did a t-test for the same thing, control group and treatment group, I'm sorry, here the p-value is almost 0. So, you know, we're getting something a little bit different. But, oh, the reason why is because I was only using the first 20 values here. All right, I was like, what is going on? Okay, let me just do this again. We'll shuffle that up. Just taking its time, okay, because it's a lot more data to crunch. All right. Mean absolute value of the differences. Oh, what is going on? Oh, no wonder. Let's see, bad code. All right, I have to create the pool as control group and treatment group. All right. All right. Now it should work. Let's try this. Okay. So it runs. I hope now. Okay. Our observed difference is -10. The mean. So this happened. How often was the absolute values of our differences greater than 10? That happened 0 times. And when we do a t-test for our data, it says it's going to happen on the order of 0 times as well. Okay. I can kind of just play around with this. You know, what if what if the true difference between observations is only 2? 100 versus 102. You know, will a t-test pick that up? A t-test picks that up with around and gives us a p-value of 8%. Okay. So it doesn't quite detect it, and but let's kind of see. You know, we get something around 9% here. I mean, what happens if I just do greater than? Yeah, no, same. Okay. Okay. So anyway, these are randomization test examples here. Okay, is that all right? Questions on this? So we saw 2 kinds of randomization tests. On Tuesday, we saw randomization tests for kind of proportions, categorical variables, using like who yawns and who doesn't yawn. So those were true falses, and we were doing categorical variables. Here's just a silly example with numeric variables. Okay. I'll post all of this code up as well. Okay, on the other hand, we've got the Bootstrap test. Okay, and this is kind of your regular Bootstrap test is kind of the non-parametric Bootstrap. And this is kind of the regular Bootstrap. So when people talk about the Bootstrap test, or they're generally referring to a non-parametric Bootstrap test. Okay. Let's see. I've got some notes on this. Okay. So bootstrapping kind of comes from the phrase to pull yourself up by your bootstraps. I don't know if this is true, but apparently there's a German folktale where you know, the hero got stuck in the swamp, and to get himself out, he pulled himself by his bootstraps. Okay, so, but anyway, it's the idea of kind of resampling our data without the need for additional data. Okay, so if we think about how does a normal t-test work, a regular old t-test work, we're putting on the assumption that the population you know, looks like this, and that the sampling distribution follows a normal distribution, and that's why we're able to use the t-test. In other cases, you know, we might have a sample of data and we might want to compare that to the population, and we want to know, you know, how often does this happen. Okay, so with bootstrapping, what we're basically, not the parametric, in the non-parametric bootstrap, what we do is we make the assumption that the sample we have is representative of the population. Okay, so let me just kind of contrast this to the randomization test. The randomization test is used when there's random assignment in the process to create our data. Okay, the bootstrap test is going to be used when there's random sampling in the process of obtaining our data. Okay, so the bootstrap test, we can use bootstrap, we can use the bootstrap if there's random sampling in the process of obtaining our data. Okay, so that is to say some kind of, you know, surveys with random selection. In the randomization test, the assumption is exchangeability. In the bootstrap test, the assumption is representativeness. I'll just call this representation. Okay, we make the assumption that our sample is representative of the population. Representative of the population. Okay. So in the randomization test, we assumed, you know, every possible permutation of the data is equally likely. Here, we're going to make the assumption that the random sample that we have, this sample is representative of the population. Maybe that's a good assumption, maybe it's a bad assumption, okay? If it's a bad assumption, then everything will fail, right? But here, we're gonna make the assumption that our sample is representative of the population. And so, with the bootstrap test, what we're trying to go for is we wish to be able to sample directly from the population to get the sampling distribution of whatever sample statistic we have. So if we're interested in the sample mean, we wish we could just resample the population many times to get the sampling distribution, okay? So in the bootstrap test, you know, our dream wish, and I write dream wish because this is not possible. Our dream wish is to resample the population many times to get the true sampling distribution. Okay, so we wish this is the true population, and we wish we could just get sample 1, which produces x bar 1. We get sample 2, which produces x bar 2. Sample 3, which produces x bar 3. So on and so forth, okay? To sample, I don't know, 10,000 to give us x bar 10,000, right? And then we would combine all of these and we would get, you know, this is the sampling distribution of x bar. This is what we want, right? So we wish we could get this sampling distribution of x bar and figure out where our x bar lies in the true sampling distribution, right? We wish, that's what we wish we could do. Okay, but we don't have access to the true population, right? We don't know what the true population is. We can't just resample the true population. So instead, so this is our dream wish. With Bootstrap, this is what we do. We assume our sample is representative of the population, right? This is the assumption that we are making. We assume our random sample of the population, okay? So what we do is we take our current sample, okay? And then we just duplicate it like 1,000,000 times. Or like maybe infinity times, okay? So we just clone the sample. I don't know, many times. Okay, and then we throw all of those together, and now we have like a pseudo population, right? Does that kind of make sense? So we have a we have just a random sample, and we're going to say, I think this is representative. So let's just clone it like a bajillion times. And this is now our pseudo population. Okay. So if your current sample is not representative, then your pseudo population is going to be terrible also, right? But this is what we're doing, right? So because we don't have access to the true population, so we just take our current sample, we clone it a whole bunch of times, and we say this is our pseudo population. And then we go through the process. And then from here, we create our sampling distribution. Okay, so we go, all right, here's sample 1. And we get, x bar. And then here's sample 2. And we get x bar 2. And here's sample 3, x bar 3, dot, 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 until we get, you know, sample 10,000. And x bar 10,000. And then we get our, you know, our bootstrapped sampling distribution. Okay, which can then be used for hypothesis testing. Does that kind of make sense? So the true sampling distribution comes from the idea of resampling the population many times. Every time you draw a sample, you record a new x bar, you keep track of every single x bar you get, and that produces your sampling distribution. Okay? With Bootstrap, we don't have access to the true population, so we just say, well, I've got one random sample. I'm going to assume that it's representative, so I just clone it a bunch of times. So now I have a whole bunch of values, and that becomes my pseudo population. Is that okay? All right, and so instead of actually taking your sample and cloning it a bunch of times and creating a bigger thing called the pseudo population, we can do effectively the same by just sampling with replacement. Okay, so if we sample with replacement, meaning you select one and then you put it back into the sample and then you shuffle it up again, that is effectively doing the same thing as taking your sample, cloning it, and creating a pseudo population. Okay. Sampling with replacement is effectively the same as cloning the sample many times to create a pseudo population. Okay, so the bootstrap, in effect, just looks like this. Current random sample, and then sample with replacement to make sample 1, with replacement to get sample 1, and you get x bar 1. Sample 2 produces x bar 2 with the replacement all the way to sample, you know, sample n to get x bar n. So you don't actually have to duplicate your sample, you know, a million times. Okay, you can just sample with replacement, and that's effectively the same. Okay, and so we do. So when you write the code, it looks almost very similar to randomization test. Okay, the only difference is in the sample function, you put in the option replace equals true. Okay, and then so now you're sampling with replacement, and then it suddenly becomes a bootstrap test. Okay, and because they are so similar, students will get these mixed up. But again, the key is randomization test when there's random assignments. So you're thinking the data came from an experiment. Bootstrap test when there's random sampling. So your data is coming from like a random sample or a survey of some kind. Okay. All right, let's do an example here. I think this shows up in your homework, but I'll go ahead and we'll work through it. All right. So Bootstrap tests. Oh, before I get into that, I kind of just want to highlight a couple articles. All right. So so you make sure you do your reading from the textbook, comparing groups. Okay, and then so a couple years ago, ASA, American Statistical Association, this is kind of like the professional organization for statisticians, they released a statement on p-values. And I don't know if you're aware, but there's been a lot of controversy surrounding p-values, okay? Maybe you knew this, maybe you didn't, okay? And people are arguing about stuff, right? Because, well, in Stats 10, what did they say you should use for alpha? Like 5%, right? And then if your p-value is bigger than 5%, what do? Do not reject the null. And if the p-value is smaller than 5%, you do reject the null, right? I don't know if your statistics teacher told you, but that 5% is kind of an arbitrary number, right? 5% is a little bit arbitrary. Probably we selected it because we have 5 fingers on our hand, or I don't know. You know, it's a little bit arbitrary. It's like, it's supposed to be small, but not too small that you're never rejecting the null and something like that. So we picked 5%. And so this has been around for quite some time. And people have been noticing that a lot of research being published in journals, generally not written by statisticians, but people who, you know, they're biologists or geologists or psychologists or political scientists by trade, who took some statistics courses in order to do the research and the math. They're finding that a whole bunch of these articles are being published with p-values of 4.9%, 4.8%, 4.7, 4.95%, you know? It's just like they barely made the 5% cutoff, and so they're publishing, right? Because a lot of these journals are kind of like, we want to make sure your p-value is less than 5%. So they do their thing, and then when they get a p-value smaller than 5%, they're like, yes, this is great, and then they send it off to for publication, right? And that's not how it's supposed to be, okay? It's 5. The p-value probably should be something around 5%, but it was never intended to be this harsh 5%. If it's, you know, 5.1% no and 4.9% is good, okay? It was never meant to be that, and so the ASA, American Statistical Association, released a statement on this. I hope this link still works, yeah. Kind of the statement on p-values, context, process, and purpose, and you should read it, okay? Just kind of the acknowledgement of what p-values should be, okay? There's also another article on 538, which is a great website for sports and political analysis from a statistical perspective, and it just kind of talks about science being hard and this notion of p-hacking and stuff, okay? How often is something just coincidence versus All right. Is this the one? P-values? Yes. Okay. So this is. You guys ever go to XKCD Comics? All right. You should all read this comic now. Okay. A web comics of romance, sarcasm, math, and language. It's like. All right. Okay. This is everybody here, right? Okay. So, let's do this, right? Okay. So it says jelly beans cause acne. Scientists investigate, and then it says we found no link between jelly beans and acne. Okay, and so they go p-value being greater than 5%. It says that settles that, and then the person objects, and it says I hear it's only a certain color that causes it. Okay, and so they call the scientists, and then they do all right. So they say we found no link between purple jelly beans and acne. The p-value is greater than 5%. We found no link between brown jelly beans and acne. P-value over 5%. No link between pink jelly beans, no link between blue jelly beans, teal jelly beans, and all of these things. The p-value is greater than 5% in all of these, right? We found no link between cyan jelly beans and acne, and says we found a link between green jelly beans and acne. The p-value is less than 5%. And then they go on, we found no link between all of these other things. And then the published news is green jelly beans linked to acne, right? 95% confidence. Only 5% chance of coincidence, which is kind of, maybe this is how science is done these days, all right? And this is kind of the objection to p-values in general. If you're using a p-value of 5%, which means, in general, 5%, there's still a 5% chance of coincidence, and these things are going to get published because we're not thinking properly through the process. Anyway. If you want to call yourself a statistician, definitely you need to have a proper perspective on the p-values and stuff. So anyway, read these things. Okay, we're going through. Wait, this is not the homework, is it? Is that the homework I put up online? Oh, jeez. Maybe I made a mistake. Let me check. I think. Here's your R Markdown template. I hope this is okay. Oh, I guess I messed something up here. All right, task 2 randomization tests, task 3 randomization. Oh, I guess there's nothing to do for. Okay, so here's task 1. All right, I decided to change this part, and I forgot to delete these lines of text. So if you're confused about this Mythbusters thing, you can ignore it. Okay, so here's the randomization test homework, randomization test from the textbook, Bootstrap, and here's our worked example. Okay, so I'll go ahead and I'll work through this worked example in class just because I think some of it requires a little bit more explanation. Okay, so anyway, there is a package called Bootstrap, right? And I guess during this time, the researchers decided to look at 82 law schools in the U.S. Okay, and there's probably more law schools, but we're going to say that this is the entire universe of all law schools. Okay, Law 82 represents the universe of law schools. Okay. And here we have two variables, LSAT score and GPA, okay? And we wanted to know, is there a correlation? So it's just the average LSAT score and the average GPA of the students admitted to each of these 82 law schools. Okay, so so I don't know. So there's different, you know. Is anyone planning on going to law school? Some of you, maybe, maybe not. Okay. Well, anyway, let's just create a plot here. All right. I don't even know. I think the LSAT has changed. What's the range on the LSAT now? Does anyone know? Nobody knows. I guess we could ask Google, but okay. So this is, you know, each dot represents a different law school, and we're looking at, you know, is there a relationship between LSAT score and GPA? And this is the average LSAT score of everybody admitted to the school and the average GPA of everyone admitted to the school, right? So this is like the super competitive school. Maybe this is like Harvard Law or Princeton Law. I don't know, okay? But I'm imagining if you look at the admission, you know, the average LSAT score of everybody admitted to Harvard Law, I imagine it's very high. And if you look at the average GPA of everyone admitted to Harvard Law, I imagine it's also quite high, okay? So, you know, Harvard, Princeton, Yale, right? Those are your things. And then I don't know what school this is, but this one, this is like, okay, your backup school, they'll take you with you know, a low LSAT score and a low GPA. And then, you know, if you know what school this is, and you go to your lawyer's office and you see graduated from this school, you'd be like, I don't, you know, maybe I don't want this lawyer. Or I don't know, you know. Maybe LSAT and GPA has nothing to do with how good or bad of a lawyer you are, but anyway, is there correlation? It seems like there's positive correlation, which makes sense, right? You imagine in general, schools that are competitive will want high GPAs and high LSAT scores. Your average schools will take average GPAs and average LSAT scores, and then your less competitive schools may be lower in general, okay? I don't know, all right? And so maybe this school over here emphasizes GPA a little bit more than LSAT score, and you know, this school over here emphasizes higher LSAT scores and doesn't put as much emphasis on GPA. I don't know, okay? This is what we have, right? So this represents the population. This is everybody, okay? Now, the true correlation between LSAT and GPA in the population of all 82 schools is around 0.76. That's the true correlation between LSAT and GPA. Okay, here we can take a random sample of 15, okay? And that's what, if we look at law is just a random sample of 15. So if I, let me, xlim will do 450 to 715, and ylim will be equal to okay, so here is, this is 1, okay? So this is all 82. And I just want to use the if I go to the data frame law, this is just a random selection of 15 out of the 82. So this is all 82, and here we randomly select 15. And we're going to say this 15 is representative of everyone, okay? And we can see, there's something in us that goes, oh, that doesn't feel quite right. But that's effectively what we are doing with Bootstrap, okay? With Bootstrap, we're saying, here I have a random sample, and it's going to be representative of everyone, right? Which is not true. But that's what we're doing, okay? When we do Bootstrap, okay? So you can already start to imagine some of the limitations of Bootstrap, right? It's kind of like, I don't know, Congress or something, right? Like you got 435 representatives in the House, and they're supposed to be representative of how America feels about politics, and I don't know. All right. Anyway. Okay. And we can see, just like what would happen if I selected a different sample, right? So here I'm going to call this law sample 1, and out of the 82, I'm selecting 15 of them, right? So here I do sample 1 through 82, select 15, and this will select 15 random rows out of 82, and then we're going to just select the two columns 2 and 3. And so now let's create a plot of this. And just do law underscore sample 1 and take a plot there. What happened to the other plots? Did they disappear? Alright, so this is everybody. This is one random sample. Here's another random sample, okay? And if we ask, what's the correlation here? We get a correlation of like 95%, okay? Just because invalid plot index, that's sad. Okay, so here's everybody. Here is here it is, okay. And here's just the 15 that got selected, okay? And these happen to just be aligned very closely to give us a correlation of 0.95, right? Here, if I do another random sample, I don't know why my plots are disappearing on me, but here's law sample 2, okay? And so this is just another random subset of all 82. Here's all 82, and this is just, we selected another 15 at random, okay? And in each of these cases, when you do Bootstrap, you're saying, I'm assuming my 15 is representative of the population. And we're seeing, maybe this isn't the best idea. But I don't know, we might not have any other choice, okay? At some point, this is the thing of all statistical analysis, and this is why, I don't know, this is why my feelings get hurt when I tell people I like statistics. So, right, I don't know if you had a conversation with people, right? They ask you, what are you studying? What do you teach? I tell people like, oh, I teach at school and I teach statistics, and they go, oh, statistics, right? I hated that class or something, and I'm like, oh, this is my life, and you're telling, this hurts my feelings. But anyway, and then, so I love statistics, right? And so I try to explain what statistics is about. And then somebody will often say like, yeah, well, with statistics, you can kind of say whatever you want, right? You can always prove whatever you want to say. And then I'm just like, not really, but maybe if you didn't understand statistics, maybe you would be fooled by someone who's presenting statistics. But anyway, this is the reason why people might say that about statistics is because at some point we are always making assumptions about the population, right? Because the central idea of statistics is you only get to see a sample of data, and you're trying to then generalize to the population, so you have to make some assumptions between what you have and everything else, right? And so depending on what assumptions you are making and who's making those assumptions, people can indeed come to different conclusions, right? And sometimes those assumptions are good, sometimes those assumptions are bad. Is it safe to assume that your random sample is representative of the population? Okay? The answer is no, it's never safe to assume that. However, you might not have a choice, right? You've spent all this money to get what you believe to be a random sample, and it may or may not be representative, right? Election polling is always trying to figure this out, right? Before an election, they always want to know who's going to win, right? And the answer is we don't know who's going to win until the day of the election. And but before then, there's a lot of speculation. A lot of money is invested in polling, and they're trying to figure out what we can do to make this candidate win or whatever. And you get mixed results because at some point somebody's making an assumption, and maybe that assumption is good or bad. So anyway, so here's just a different random sample. Let's just take a look at another one, and if I plot this one, okay, it looks like that. Okay, and each of these we're getting different correlation values. So the one that was more spread out, we had a correlation. So we have different correlation values. Okay, and so here I write that the correlation between LSAT and GPA depends heavily on the sample selected from the population, right? Loss sample 1 had a correlation of 0.95, loss sample 2 had a correlation of 0.63, loss sample 3 had a correlation of 0.82, okay? But again, to do the bootstrap, we're going to just take our random sample. So in our case, maybe we'll use the original. So I'll do plot law 82 dollars, maybe this second column, and law 82 third column. Okay, so this is everybody, and then here we'll just oh, this doesn't have the appropriate y limits, but this is just going to be the random subsample of everybody there. Okay, and so in this case, we will do our bootstrap manually. We're going to do 500 replications. Okay, so I think in the examples I did like 10,000. We can do 10,000 if we want to, but we're going to just take our 15 law schools in our random sample. Okay, and then I'm going to create a vector called results, which is where I'm going to store my values. Okay, and then just for reproducibility, I will set a seed. Okay, and what we are going to do is, so this is my random sample of 15 values, and from that I'm going to create something called an index. These are going to be the index of the values I'm going to choose. Okay, so here n is 15. So if I do sample 1 through n, size equals n, replace equals true, this will produce a random selection of the integers 1 through 15 with replacement. So here we see the number 4 gets selected 3 times, the number 2 doesn't get selected at all, 1 gets selected once, and so on and so forth, right? Because effectively I took the numbers 1 through 15, I duplicated that a whole bunch of times, and I said, from this giant pool, this pseudo population of the values 1 through 15, select 15 values. Okay, so that's sampling with replacement. Okay, so this is going to be my vector of index. Okay, so I'll just say index is going to be the. So here are the indices I'm going to select. Then I take my data frame, and I take the LSAT column, and I'm going to select the values corresponding to these indices, right? So here are the original 15 values, but here I'm going to select value 4, which is 578. I select value 6, which is 580. Okay, so we subset LSAT using the sampled indices. Okay, and because R allows you to put in the same number multiple times, these are going to be the random values resampled here. Okay, and we do that with LSAT, we do that with GPA, and then we're going to just find the correlation between those two values. Okay. Is there a question?
Why don't you use the law and LSAT into like the first parameter of sample?
It Oh, into sample directly?
Yeah.
Yeah, we can do that. Well, so here's the thing: I want to make sure that that I'm selecting. If I select row 4 from LSAT, the LSAT column, I also want to select the corresponding row 4 from the GPA column. Okay, so I don't want to throw all all 15 LSAT values and all 15 GPA values and just say select 15 with replacement from this column and 15 with replacement from this column. Okay, so I'm saying select 15 values 1 through 15 with replacement, and we're going to use that to make sure we select 4 from this column and 4 from the other column. We're going to select row 6 from this column and row 6 from this column. Okay, so using the index, I think, helps with something like that. Okay, so we say these are the index, or the rows that we're going to select, and from there we subset each column according to the index, and then we calculate the correlation of the things we just did. Okay, does that kind of make sense, what we're doing here? And then I just do this 500 times. So I'll go ahead and I'll do this. Okay, and then we can get kind of the standard deviation of the results that we get. We can look at all the different correlation values. So if I look at results, I have 500 correlation values. I can create a histogram of this. Okay, and we can see a lot of the times we're getting correlations around 0.8, but sometimes we get like crazy low correlations and so on and so forth. And here we're getting a standard error of around 0.135. Okay, so how good is any one given correlation? Okay. Okay, so that's kind of the manual Bootstrap right there. If you talk about doing Bootstrap, a lot of times people use the package boot. Okay, so within R, there's something called package boot, and package boot, the results can then be fed into other functions. So other functions use the results of package boots. If the function boot produces exports an object of a I think class boot or something like that, and then there's certain methods associated with it to create confidence intervals and the like. So anyway, when you use package boot, you have to create a function to calculate the statistic that you want. Okay, so in our case, the statistic that we are calculating is called is the correlation, right? So here I'm going to create a function called correlation function, and the functions we create are always a function of the data and the index. Okay, so in our case, the data will be our random sample of 15 law school entries. Okay, and then the index is provided by the boot function, and it serves the same purpose of the index when we did manual Bootstrap. Okay, and so effectively, when you use package boot, it will generate the index and pass it to the function that you write. Okay, and so the index will be the values 1 through 15 sampled with replacement. Okay, so basically we take our data, which is going to be the law school data frame of 15 values, and then with that, in our function, we subset the data using the indices. So I'm going to take law, subset it based on the indices. From there, I extract LSAT and GPA, which are the according columns, and then the value we return in the function will be the correlation between LSAT and GPA. Okay, so the correlation function, it's going to take as one of its input the data frame, and then as the other input argument that it takes in, will be the index. Okay, so here the index is this, and so if I ran this index right here, and I said calculate the correlation of this and this, it would give me 0.940211. Okay. If I run the correlation function here, as defined here, I would pass it. The way I would call it would be correlation function. I would give it law and the current index, and it runs it through and it returns the same values. Okay, and or more concisely, you can compact this down just to this, but it doesn't matter. Okay, and the way you use boot is you just write boot. You give it the data that you want to use, in our case law, and then you give it the name of the function that you wrote, correlation function, and you say run it 500 times. Okay, so here we'll load up library boot. We'll run the correlation function, and then we can ask for the results of Bootstrap. Okay, and it says this is what we calculated. The standard error is around 0.1335738. We can get the standard error ourselves by asking the standard deviation of the results $t. Results is a list. We can ask what is the structure of results. Oops. Okay, and it's a big list. It kind of tells us, what is the value of the function if we run it through the original data. If the index that's selected is just 1 through 15, what are all the different values it generated? So we can ask, what's the histogram of results $t, and this will look kind of like all the values that we observed, similar to our histogram. It's a little bit different. Okay, it includes the original data frame and a bunch of other stuff, and this is of class boot, okay, of which there are other methods, right? So when I ask for results, it does this because there is a print.boot method. It's not print.boot. Okay, well, when we ask to print the results, it's calling something to print it this way rather than the default structure here. What is it doing? Okay, well, I'm not sure, but okay. So that's how we would run this with library boot. Okay, and so once you have the correlation function written up, it's not too bad running Bootstrap. Okay, so we can say, give us the results of one of our things. So this is ordinary non-parametric Bootstrap. Here's for one of the random samples. If we did law sample 2 and we asked for this, we would get something different. So all of these things, we can see some of the weakness in using Bootstrap, especially because you're making that very strong assumption that your random sample is representative of the population, which it may or may not be, depending on which aspect of the population it is that you're looking at, right? So, okay, so here we have this. So let me give you just a few more examples of how non-parametric Bootstrap can be written. Okay, so let's just do. So you have that in your homework. Let me just do like some other test here. Okay. So let's say you take a random sample of, I don't know, apples and oranges or something like this from the population, right? Okay, and so you have apples being, so we'll have random sample of apples and oranges, okay? And so what's the average weight of an apple? Our norm, average weight of apple. Oh, I think we already did this, right? It was 1 Newton, 100 grams. I remember this. Okay, so we'll say we get, I don't know, we'll do this, okay? Apples, average weight of orange, 140 grams. Oh, that's considerable. All right. There's no comparison here now. All right, so we're gonna have 15 apples and 15 oranges here, okay? And so how would we do a bootstrap test? Okay. So what we would end up doing is we would resample our data with replacement, okay? And when we resample, so here, let me just write this out. Okay, so the null hypothesis is mu1 is equal to mu2, right? And then we'll say the alternative hypothesis, well, maybe mu1 is less than mu2, okay? Where mu1 is apple mean, mu2 is orange mean. Okay, so if null hypothesis is true, both the observations can basically come from one population. Okay, and so so here we're going to just create a pool, which is going to be the apples and the oranges just thrown together. Okay, and then so now you just have this pool of, I don't know, I guess fruits in these paper bags, and you don't know what's inside, right? And then we're going to sample. We're going to take our so we have our 15 apples and our 15 oranges, but we're going to hide them in paper bags. Okay, so we don't know what's what. Okay, so now we have 30 paper bags with fruits inside, and then we throw this into our cloning machine. Okay, and we clone this 1 billion times, so now I have 30 billion paper bags. Okay, and then we're going to resample some of these things. Okay, and if the null hypothesis were true, that apples and oranges have the same mean weight, okay, then I can pick 15 of these bags, put them into group A, and 15 of these bags and put them into group B, okay? And whether I call this apples or oranges, it doesn't matter because they have the same mean weight, right? So, so basically, our resample will just be sample what we want. How do we do sample? That's not what I want. Okay. Geez. Okay. I want sample. Okay, sample the pool, right? We're going to sample our pool size equals 30, replace equals true. Okay, so we're going to do that. we're going to take the first 15, throw them into group A, the next 15, and throw them into group B. Okay, so if the null hypothesis is true, the observations can basically come from one population, which is going to be our pooled values. Okay, then we resample this. We select 30 from our pool with replacement. Okay, so it's effectively taking our 30 mystery fruits and then running them through the cloning machine. Okay, and then we resample those. Then we get our difference is going to be the mean of group A minus the mean of group B. All right, and then we want to know how often is this difference greater than the observed difference. Okay, so I just have to do this for I, and so we'll create a results vector. No, I'm sorry, a difference vector. We'll repeat NA 100,000 times for I in 1 through length of difference. Run this loop. Okay, so this looks almost exactly the same as the randomization test code. The only key here is that we are doing replace equals true. Okay, and it's a small difference, but the implications of the difference here is quite big. Okay, one here, this replace equals true means we're assuming these themselves are random samples. Okay, so these are this, well, I guess I rewrote that. Random sample of apples and random sample of oranges, right? All right, so let's just set some seeds for reproducibility. We got apples and oranges, so we'll pull them together. Then we resample these, okay? Our observed difference is going to be the mean of apples minus the mean of oranges, okay? So we get an observed difference of negative 39.95, okay? And then we want to know, all right, how often, let's just take a look at our histogram of differences that we get, okay? We almost never get, I don't think we ever got something greater than negative 39, but let's just see. All right, so we will see the mean of how often is our observed, is the absolute value of difference greater than or equal to the absolute value of the observed difference. How often did this happen? Okay, 0 times. I don't know. I'm curious. Will this ever happen? Probably not. If I do this 1,000,000 times, will it happen even once? Probably not either. Oh, it takes a while when you ask for it 1,000,000 times. I guess it should take 10 times longer. All right. It still happens 0 times. Let's pretend we were dealing with like huge orange apples here. All right. And it detect a difference of okay, so if you were dealing with big apples with an average of 130 versus an average of 140, and then you do this and you throw some into, then you get a difference. Our observed difference happened to be, our observed difference happened to be small in this case, only 6.75. So we get this around 17% of the time, right? So, as always, the question is, here are, my values of apples. And is this representative, right? So the population would be, if I did like, So the population will look something like this. And the question is this representative of this, right? So if this is the population, let me just do xlim is equal to 92. It looks like 170, okay? You know, is this representative of that? I don't know, right? And then the same thing with if we look at our sample of oranges, okay? Is this going to be representative as well, right? We need to go to 180 for this one. All right, so here we've got our histogram of oranges, whereas the population for oranges, looks something like this. Oops, I did something wrong. Okay, so if this is the population of all oranges, is this random sample representative of this? Probably not, but anyway, that's what we have. Okay, and so in the Bootstrap test, you pull all of your values together again, you shuffle them up with replacement, okay? Because under the null hypothesis, where mu1 is equal to mu2, you're basically saying they're coming from the same population mean. So you throw them together, then you just reshuffle them. You say some of these are in group A, some of these are in group B. Okay, and we want to know how often do we get a difference like the one we observed. Are we okay on this? Okay, so this is, let me just redo this using library boot as well, okay? Library boot, okay. So here, we've got our pooled data. This is all the values we're going to use, our 30 values. And so our difference function will be a function of data and index, okay? You always have to create a function of the data and the index. And so basically you subset your data based on the index. In this case, our data is just a vector, and our index will just be a vector as well, okay? And then we'll call this group A, will be the first 15 values of our subset data, and group B will be the next 15 values of D, and then the value we return is going to be the mean of group A minus the mean of group B, okay? So it's very similar to this, okay? Except the resampling part is taken care for you. You have to write a function as a function of data and index, okay? So always write a function of the data using data and index as the arguments, okay? And then we just ask boot, here I'll call this results, will be boot. We give it the data, which in our case is the pooled data, using the difference function, and under boot, what is the letter for replicates? R is equal to, I don't know, we'll do 10,000 here. Difference function not found, okay. Okay, now you can find it. All right, so now it's done. And then you can make a histogram of the results, $T. These are kind of your Bootstrap replicates that you see. You can see your empirical p-value will be results $T mean of, we'll say, the absolute value of the results of t being greater than the absolute value of your observed difference. Okay, so here we get p-value of 63%. What's my observed? Did I mess something up here? Oh, observed. I used a different word here. Okay, so there we go, 17%, which I think matched. Well, we got something over here. Yeah, something on the same order. Okay, and well, anyway, there you have it. Okay, so here we stored our differences. When we did it manually, we stored it in this vector diff. Okay, and when you use the function boot, it's going to store it in $t of the output object. For a two-sided test, and then for a one-sided test, it would be something like there's your one-sided test results. All right. Are there questions on this? Bootstrapping here? How do we feel? So we'll say this stuff is fair game for the final exam next week, okay? And I'll make sure to post all of this code and the stuff up online, and then we'll do stuff on Tuesday. I don't know. Should I take attendance? No. No. All right. Okay. Well, we'll wrap it up here then, and we'll see you guys next week. Have a good weekend. Good luck, as I don't know, it's already 5th week. Oh, I think student evaluations have opened up. All right. I hope you've at least kind of enjoyed the course. And so if you have, please be sure to fill out the student evaluation. Give me a good review. If you're also willing, please consider leaving a review on some place like Bruin Walk or Rate My Professors. It's always helpful. For me, I do read all the comments that come through after grades and stuff have been submitted. So please fill out your student evaluations. All right, thanks guys. Have a great weekend.